So recently I heard for the very first time, you may be familiar with this expression already, but it was the first time for me, the phrase "dollar to a donut." I was just walking by the bus stop where all the good conversations happen, and I heard one guy say to another guy, "I'll bet you $1 to a donut he won't make that mistake again." And that phrase just kept getting stuck in my head over and over again. Dollar to a donut. That's a stupid expression. For starters, you're talking a lot of smack for a guy who only wants to lay down $1. Come on, pony up. Also, I don't buy a lot of donuts these days, but last I checked, they usually cost more than $1. I mean, even the Krispy Kreme regular glaze, like what, $1.50, maybe $2? So not only are you only willing to bet $1, but you're playing 2-to-1 odds in your favor? Now, that's stupid. That's a sucker's bet, and I'm not playing it. Get out of here. Go buy your own donut. Oh, wait, you can't. You only got $1. Okay, so by this point in the semester, you've talked about equilibrium, you've talked about acid-base behavior, and about pH. If not, I don't know what you're doing watching this video, but just go back and wait. You can come back to this later. But if you have, then we're starting to reach the point where a lot of that stuff is all starting to come together in one big old thing. For starters, you start to get into weak acid equilibrium, and you begin to notice that no matter which weak acid we're talking about, they all seem to follow the same type of Bronsted-Lowry acid behavior, which is, that acid reacts with water to give you hydronium and whatever the conjugate is, the conjugate base. And so the equilibrium constant for any Bronsted-Lowry acid is going to be the same. It's going to be hydronium times the conjugate over the original acid. Remember, we don't include water because water is a liquid. Liquids and solids aren't put into any expressions of Kc. So this equilibrium constant is so common for Bronsted acids that we give it its own special little symbol, Ka. And we call it the dissociation constant, or the acid dissociation constant. But don't let the new name throw you. This is still the same equilibrium constant as before, and we pretty much use it the same way we used equilibrium constants in the past. For example, one way you can experimentally determine an acid dissociation constant is by making a solution of that acid and just measure its pH. For example, let's say you have a 1 molar acid solution and you measure its pH to be 4.2. So again, we start with the Bronsted-Lowry reaction, and we'll build an ice table like we did a lot back in the equilibrium chapter. So rho I would be the initial concentrations, and for any concentrations of an acid, we always assume it's what we call a formal concentration. The concentration before any of this equilibrium stuff starts. And people will wonder, well, how do we know whether it's equilibrium by the time you measure the pH? By the time you make the solution, stir it, and stick the pH meter in there, it's achieved equilibrium a long time ago. So that's usually not a problem. The acid concentration is initially 1 molar. Water is a liquid. We don't care. And for our two products, we're going to, again, if this is our formal concentration, before any of this happens, we'll assume the concentrations of both to be 0. And I know earlier when we talked about pH, we talked about autoionization and how there's always some hydronium and hydroxide present. There's not enough under normal conditions for us to worry about it. For neutral water, it's 10 to the negative 7. Unless you're doing calculations out to the 6th or 7th decimal place, that little bit of water due to autoionization is negligible. So if we have nothing on the product side, we've got to shift to the right sum. So we're going to lose X amount of acid and X amount of each product. And it's all plus X or minus X because all the coefficients are 1. So rho E would be the initial concentration of acid minus the amount lost in the shift. Each product is X and X. So next we take the information we have in row E and we plug it into our expression for Ka. So again, every equilibrium or acid dissociation constant is the same. Hydronium times conjugate over the original acid. So from row E, we know that the two things on top are X and X, or we're going to call that X squared. And our initial our equilibrium concentration of our acid is 1 minus X. Now, back in the equilibrium chapter, we would, solve for X, but here we're trying to find Ka. So in order to find Ka, we need to know what X is. But remember, we have the pH of this solution, and the pH is equal to the negative log of the hydronium concentration. In this case, the hydronium concentration to equilibrium is equal to X. So we plug in our pH and solve for X using a little bit of log math, which we'll skip here for the sake of time. So X turns out to be 6.3 times 10 to the negative 5. So now we go back to our expression of Ka, plug in our value of X, and that will give us a Ka of 4 times 10 to the negative 9. But what happens a lot of times is you know the value of Ka because you know what acid you're working with, and most of the common acids, their Kas are well known. So what you'll do instead is you'll make a solution and you'll want to figure out what the pH of it's going to be. For example, let's say we have a 2 molar solution of hydrofluoric acid, and the Ka of that is usually 7.1 times 10 to the negative 4. We can figure out the pH of it using basically the same sort of ice table math we just used a second ago. Again, we start with an ice table. Our initial concentration is going to be 2 for hydrofluoric acid, because again, we're assuming that's the formal concentration. And if we ignore autoionization, both products are 0. So just like before, the shift is going to happen to the right. Lose X amount of acid, gain X amount of product. So at equilibrium, it's our initial concentration minus X for HF, X and X for our two products. Now take all this information that we know so far, plug it into our expression of Ka. We know the equilibrium constant this time, and like before, according to row E, we know that both products are X, so X times X is X squared. And on the bottom, we know hydrofluoric acid's concentration is going to be 2 minus whatever X is. So for this problem, this is exactly like a problem we did back in the equilibrium chapter. And one thing we did then, especially when we started working with small values of K, is we solved by approximation. So we can assume that whatever the concentration, whatever your equilibrium concentrations are, given how small the equilibrium constant is and the size of our concentration, initial concentration, it's probably going to be a safe assumption that 2 minus X is going to be approximately 2. Again, when you're around -4, -5, and your initial concentrations are around 2, it's often a gray area, but like I always tell folks back in the equilibrium chapter, when in doubt, go ahead and try approximation anyway. If it works, you've saved a lot of time. If it doesn't work, then you really didn't lose that much time trying. So here we'll try to approximate 2 minus X to 2, and that makes solving for X a lot easier. And that gives us an X of 0.038. And if we check our approximation using the 5% rule, 5% of 2 is 0.1. Our X is less than that, so we're good. So again, just like before, X is equal to our hydronium concentration, and our pH is equal to the negative log of our hydronium concentration. So now we know what X is. We plug in our value for X and take the negative log of it. That gives us a pH of 1.4, which is in the acid range. So barring a calculation error, we're on the right side, or technically the left, the proper side of our pH scale. So let's try one more. So we just calculated that a 2 molar solution of this acid should have a pH of 1.4. But let's say you actually need a pH of 2. Now, what concentration should we use? So again, we're going to start with an ice table. When in doubt, start with an ice table, see where that takes you. Plug in what we know with row I. We don't know the concentration that we're going to need, so we'll just call that Y since we use X for other stuff usually. Again, 0 and 0 for our two products. Row C, just like before, we got to shift to the right, and everybody's 1 to 1, so it'll be minus X on the left, plus X for our two products. And at equilibrium, it's going to be whatever that initial concentration is, minus X, and just like before, X and X for our two products. Now, we once again take what we know up to this point, plug it into our equilibrium or expression for Ka. So we know the Ka is 7.1 times 10 to the negative 4. That's known for this acid. Again, our concentrations for our products are X and X, so X squared on top. And for our original concentration, or original acid's concentration, we know it's Y minus X. So again, to figure out what Y is, we need to know what X is. But we have the pH, and like our first example, the pH is equal to our negative log. pH is equal to the negative log of our hydronium concentration, which means it's equal to the negative log of X. So if we want a pH of 2, X is going to need to be 0.01. So if X needs to be 0.01, we go back to our Ka equation, plug in that value of X, and solve for Y. And that gives us a Y of 0.15. So if we make a 0.15 molar solution of hydrofluoric acid, its pH should be around 2.0. So hopefully you're starting to see that a lot of these Ka/pH problems look really similar as far as the setup goes. I mean, you start with the same ice table every time, the same Bronsted-Lowry reaction. Acid and water give you hydronium and whatever the conjugate is. Row C is the same every time because everybody's 1 to 1 to 1. Negative X for your acid, X and X for your products. In fact, if you compare all the examples we've done, or any that you may have done in lecture, or anyplace else, the only difference for these types of problems is the initial concentration of the acid, but everything else is pretty much the same. So this is one of the few places where, as we start to progress in the course, instead of things like piling on, getting a little bit tougher, I think for this type of stuff, it's actually easier than equilibrium calculations we did a couple chapters ago. And when we get to bases in the next video, you'll see that going from an acid to a base is really the same stuff with one small little difference. But we'll save base examples for next time. For now, I will see you guys later. All right, tell you what, I'll bet you $2.50 to a Snickers bar. No? All right, how about this? $5 to a box of Girl Scout cookies. Thin Mints or Tagalongs, but not Samoas. Fuck those. Coconut. Ooh. All right, fine. $10 to a Venti latte and one of those Michigan oat cherry things. No? All right, fine. $20 to a McRib sandwich, a Rockstar energy drink, and one package of Big League Chew. Cool, shake on it.